Say that again. No, Michael, tell me. Damn it, I like these jokes. It's big. We're comparing it to 5%, and I implore you, I beg you, make sure you read that properly. It's so easy to look at that when you're working quickly and think that that's what? 1%. 10, 100%. It's so easy to put the decimal place in the wrong place. That's 10%, which is bigger than 5%, which means what? What happened with our data? What happened with our data? Or, let me ask it a different way. Which hypothesis does our data agree with? This might be a better way of asking the question. Which hypothesis?
Isn't it the null?
Darza, why is it the null? I heard a null over there too. Dina, yes, thank you. Why is it the null? Dina, give me. Why is it the null?
It's greater than 5%.
When it's greater than 5%, where are we? Where are we? What are we within? The 95% confidence around what? You got it, you got it. You guys want to roll. When you're bigger than 5%, you're within the 95% confidence interval around, in this case, I called it 0, but that's standardized. What does that 0 stand for?
The average.
Boom! Whatever the average is in the null hypothesis, the 46.7%. So you didn't believe that it was 46.7%, right? You did not believe that. You think it's different. I don't know if it's bigger or less than, it's different. So what you essentially do with a hypothesis test is you set up an interval around that. Well, here's the kicker. That's where that confidence interval would have actually gone out to. -2 to 2. If you think about what a 95% confidence interval looks like, it's -2 to 2, essentially. You, at -1.64 standard deviations, fell on this side of it, which means you're within it. When the TI draws the curve, it's showing you the p-value shaded. And when that shade is bigger than 5%, that means not only did you shade the outside of the confidence interval, but also some of the inside, which means you're still within it. The only way that area shown could be less than 5% if you were outside the interval. Does that make sense geometrically? It's a geometry problem at that point. The only way for your p-value to drop below 5% would be for you to be outside the interval. You'd have to fall either on this side or this side of it to pick up less than 5% of the area. So you must have fallen on the inside of it. Which is what this is telling you. You fell on the inside. So when this is big, who do you believe? You believe the null. There's no reason not to believe the null. Remember the formal language that statisticians use? You fail to reject the null. I like the word believe. You believe this. In other words, you can't believe your claim. Remember what your claim was? Your claim was that it's not 46.7%. I don't think we can support that. Even though we got 40%, which is almost 7 percentage points lower, it's still so wide that the margin of error is so wide that we can't not believe it. So friends, we are now to the conclusion part. What do we circle?
Appears.
Okay, I heard, wait, I'm hearing two dissenting voices. Read the entire thing.
Oh, it does not appear.
Yeah.
Look, you got to make sure, and I'm going to bold italicize this now that I've heard your responses on the exam. I'm going to write this as in reference to your claim. Right? I'm writing this in reference to your claim. So read it again. It blah blah that the percentage of girls born in China is not 46%. That's your claim. So it does not appear. It does not appear that it's not 46.7. Some of you are going to say, well, that's a stupid statement. Why don't we just say it is? Right? Why don't we just say it is? If it is not, the double negative, call it is. You can totally call it that. But I am going to get you thinking in terms of your claim. And if your claim is not, we can't believe your claim. Does that make sense? There's a single negative. We can't believe your claim. There's a single negative. It's just that your claim is also negatory. Can't not. Rosie, answer that question.
I don't know.
Are you sure? God, it was 3 seconds ago. I'm sorry. I should have gone quicker. That's my fault. I should have jumped on quicker.
I do want to go over...
No, we're getting to this. We're getting to this. We're going to move to this next because what I'm going to have you guys do is I'm going to have this little... I think I had this on your quiz that I had for Thursday of last week where I said identify the types of error. If not, we'll do it right now because this ties back into what we were talking about before. Everybody okay with this? Jack, go.
I just remember you saying something about the test score 1.64.
Good! What about that?
But that was a significant marker.
It is for a one-sided hypothesis test.
Okay.
And this goes back to Will's question from last week, which I have not forgotten, which is a good one. If we were testing it one-sidedly, Danny, like you said, when you said, I think it's lower. Because she looked at the numbers and said it's 60 and 150, that's below 46.7%. If you tested this one-sided, that would still be 1.64, and what would that be?
0.05.
That would be exactly 5%, because you'd lose one of the tail. You'd lose the tail that was over here. Now it's exactly 5%, now what do you do? Now what do you do? And what's the answer I'm always going to give you? Go get more data and see if it holds up. Go get more data and see if it holds up. I find it surprising, this is my guts speaking here, that if the reported percentages are almost 47% and you're getting 40%, that's a big difference. That's a 7% difference. I find it strange to believe that if the report is actually 47, you should be getting something as low as 40. I say go get more data. If indeed you do get 40% as a center again, with more data, that will be more extreme. It'll push further away from zero. I encourage you not to believe that and make up numbers. Make it 600 out of 1,500. Make it 6,000 out of 15,000. Make it whatever you want out of whatever you want. You're going to see that p-value get smaller and smaller and smaller. Because it's showing, if that holds up, it's showing the fact that there is a significant lowering. So Jack, does that make sense? It is a marker. It's a marker for a 95% one-sided confidence interval, or it's a marker for a 90% two-sided interval. Nobody ever tested 90%, because that would put too much area in the tails. Is that fair? Good. More questions? Love that question, thank you. More questions? Okay, good so far? So, let me ask, I'm going to ask an intermediate question here and then come back. You guys are okay with putting this together based off this example? We can extract that. We'll do another one. I think we have time for one more. We know how to get these numbers off the TI, yes? And we know what this means once we have those numbers. That's kind of crucial, is making sure you know what to circle down here. Based off of what this is telling you. These? Sorry. Spent a lot of time in middle schools. Good? All right. Let's do an error analysis. Let's do an error analysis. Which we should always be thinking about this. What would a type 1 error be? Now I'm asking you to go back in time, and the reason I'm bringing this back is because this is from the Intro to Hypothesis Testing homework. And we were talking about type 1. Danielle, please.
Is this the type 1 error and type 2 error? They say the same thing.
Look at side to side. Think of it like this. One of these two statements up here would be a type 1 error, and one would be a type 2. What I want you to do is to circle which one is the type 1 error. Thank you. Yes, they both say the same thing here and here and here and here. But in one of them, one of those two verbally stated things is a type 1 error and one's a type 2 error. I want you guys to tell me which one's which. So remind me everything you possibly can about what a type 1 error and or a type 2 error is. Use old terms if it makes you feel better. False, true. Go ahead, Lindsay.
Type 1 error is a smaller p-value.
Say that again.
Type 1 error is a smaller p-value.
Good! The only time you could make a type 1 error is you could have a small p-value, which means we could not have made a type 1 error here. The only kind of error we could make here would be a type 2 error. Thank you for answering this question. We could have made a type 2 error. Thank you, Liz. Perfect. Perfect. We'll come back to that. But here's the deal. When you go into a research study, you want to identify both of them. You want to identify type 1s and type 2s and make sure you can kind of deal with both types. So what would a type 1 error have been? Supposing you got a small p-value, what would your type 1 error have been? It's a false positive, Kayla. Thank you. It's a false positive. Which means what?
Saying the birth rate isn't 46.7% when in fact it is.
When in fact it is. This would be a false positive right here. Saying that something changed when in fact it didn't. That is a false positive. Saying something's different when in fact it's not. That means you inadvertently got out of the confidence interval. You got outlier data. You got outlier data. Is this starting to ring a bell? It's about 2 weeks old now. It's about 2 weeks old. We're doing intro to hypothesis testing. Saying something changed when in fact it didn't. Now we did not make that claim based off our p-value because our p-value was big. So we could have made a type 2 error, which is saying the birth rate. Good! Saying the birth rate is 46.7% when in fact it's not. That's the type 2 error that we could have made. Because that's our conclusion. Our conclusion was that it's not 46.7. Essentially we're saying, well, I can't refute that. A type 2 error means you should have refuted it. Now, when I say you should have refuted it, you don't know that. This is probability. You're putting forth your results and saying, based on the rolling of the dice, here's what happened. But that would be the type 2 error. And we could have made that one, just like Lindsay pointed out. Here's a bit of a trick question. What's the chance of that type 2 error? Give me a Greek letter. Do you remember? It's okay if you don't remember. As beta. Thank you, friend. We call that beta. And you can't calculate it without more information. I'm not going to ask you that on Thursday. I'm going to come back to that as the course winds on, calculating type 2 error.
The first one's a false positive.
What would the chance of a type 1 error be if we could make one? What's the chance of a type 1 error always?
1 in 20.
1 in 20. 5%, thank you, sir. It's what we're basing our conclusion on, is that 5%. Thank you. Rosie and Dean, answer that question you guys are asking over there. Maybe.
For the type 2 error, okay, you said this one was a false positive, this one's a false...
Yes, ma'am. That's a false negative. This guy's a false positive. Now, see if you can make sure you understand why it's a false positive versus a false negative. What does a positive test result mean? Let's say you're taking a disease test. Like, I've had Lyme disease like 18 times. I take a test for Lyme disease. I come back positive. What does that mean? It means the test is saying I have it, right? When I go into the test, what am I hoping? That I don't have it. So I want a negative test result, which means I don't want anything to change. I want to go in there, and I want to come back out knowing I'm clean of Lyme disease. I'm clean of Lyme disease. When it comes back positive, that means what I was hoping or what I was assuming has changed. That's why this is a positive test result. When you go into a hypothesis test, you're assuming that the belief of 46.7% is good. And you're trying to see if your data shows you otherwise. We have no reason not to believe it, which means we had a negative test result. We could be wrong, falsely negative. We couldn't have gotten a false positive with our test result because we didn't get a positive test result. We got a negative test result. Fair enough? You don't often hear about false negatives being fought, for example. Take a Lyme disease test, came back negative. No, I think I'm sick. Or blowing for a blood alcohol concentration at the checkpoints. Somebody visibly drunk goes in and blows a negative test result. No, dude, I'm loaded. Arrest me. You don't hear that. You don't hear about those. You hear about the people that are getting false positives, right? That are sober and blowing VACs that are off the charts. Those are the ones you hear about, the false positives, because those tend to, not always, but they tend to have more disastrous results. Now you can have, being a rock climber, you can have pretty disastrous results with false negatives too. If you've got a company that's testing their slings for breakage, and they keep testing the slings and everything's coming back fine, and they sell the slings, and I lean back in a rappel or lean back in the chains to clean the rope, and it snaps and I fall to my death 100 feet. That's a false negative problem, because they were testing to see if slings would break, and the slings were not breaking in the test. That's a negative test result. They're not breaking. And it was falsely negative, because when I sat back and that thing snapped based off my body weight of 175 pounds, that's a problem. But you don't often hear about that. You hear about things like people testing positive and losing their jobs because they tested positive for a drug test or something like that. Or they tested positive for breast cancer, good Lord, like we studied in 243. Those kinds of things. Those are the kind of ones like, could it be a false positive? My neighbor across the street and her daughter, Addie, tested positive for Down syndrome while she was in utero. Came into a frenzy. And I sat down with her and ran the math, chance of false positive off the charts. Anyway, the thing about false positives, they tend to rack your life a little bit more than false negatives, on average. On average. So you tend to hear about these more than false negatives. Nobody gets hurt with this report, obviously, right? Nobody's dying for getting a percentage wrong. But for things like side effects of diseases and things like that, that's when things can actually have an adverse effect. Sorry to freak anybody out. You guys are very quiet also. Yes? The template, is it good? We like the template, circle what's appropriate kind of thing. You still have to do reading, you still have to understand what the hell's going on. But this way you don't have to write it out on this first assessment. I don't want that. I want you guys just being able, it's baby steps for me. We learned what type 1 and type 2 errors were in previous homework assignments. Now we're linking them into this one. But the big thing for me, at this point, the big new step is being able to write the hypotheses and extract the given statistic and p-value from that, yeah? I think that's, for me, that's the most important. Good. Yes? So this would be like, I'd say a third of the exam. Here's why I'm envisioning the exam. I'm envisioning one of these, when I say these, I mean a single proportion z-test. Another t-test. So you'll have two, essentially, homework problems, one z and one t. That'll be 2/3 of your exam, doing something like this. So very little writing down stuff, pretty much just filling in blanks and circling proper pieces. Is that fair? One z, so one proportion, one t, one average. And then the other one, I'll make like your intro to hypothesis testing, where the entire test is done and all you're doing is extracting the p-values from the research. And again, circling like you did in your homework. If you go, let me put that back. I'll get some blank looks. Let me throw that homework back up so you can see it. Remember these guys? Where I gave you, read this, extract the hypotheses.
Nothing's wrong.
Nothing's
No!
up there.
Thank you, friends. Where I gave you a lot of text. From that, you extracted the hypotheses, what type of error, define the error. I'm going to not have you define the error so much as do what we just did, which is circle the potential type of error you could have made. Yes, I like that better. I like that better. So I'm thinking like one of these, and very templatized, where you circle the correct responses. One of these, and then one t-test. We'll call that your in-class on Thursday. Gesundheit. That's it. If you want one more practice before Thursday's in class, the hour class starts with one of these, and then you go off of it. So in case you're long, back up here to show you. Week 8.
Isn't the quiz one too?
The quiz is also, yeah, I'm not sure how templatized that one is. Oops, that's 243.
That's 243.
Sorry, there you go. If you look at the 244 take home right here, I make it 12 points. They'll be worth probably more on your in-class just because there's fewer stuff on your in-class. But right there, fill in the hypotheses, test statistic p-value, circle what appears does not appear, circle which type of error is each, what kind could you have made, boom. So that's good practice, for sure. Nice and templatized, so all I'm doing is testing that you understand what the pieces are. And then we'll spend the remainder of the term together just doing more and more different kinds of tests and making sure that you can extract from that. Is that fair? And this out of class, all you're doing is dealing with this data set the entire time. I mean, the entire time. And it's more realistic. I'd rather give you fewer problems and have you look deeper at them than give you like 18 problems and just see if you can get through in like an hour. I'd rather spend time on a problem and making sure that you can extract what you need to extract. Fair-ish? Get there. Good.
Could you put up just what a t-test will look like?
Sure. Let's pull up the textbook. And just grab a t-test out of the textbook. Let me see what that's going to be. Hang on one second. That's going to be. Oh, it's low. Sorry. I just upset it. There we go. So we've got non-matched pair or matched pair. Oh! What do you guys think? You like matched pair or non-matched pair? Matched pair is where you have 2 sets of data subtracted, you get the third set, the third list using that. Let's grab that because they're pretty obvious. They jump out at you when you see those. So let's just go to here, the matched pair one, 21. Let's take a look at that. We'll compare and contrast, but I think you guys like the matched pair ones better. Matched pair 21 on page 442. Let's go to page 452. I'll type that wrong. 452. All right, number 21. 21. Let's go find it. Here it is right here. A little bigger. Actually, this is a good one up here too. You can look at that one as well. So here it is right here. This actually ties in beautifully to what you asked earlier, Rosie. We are asking husbands and wives a question. Being pleased with the way we divide responsibilities for child care. And you see the Likert scale? 1 to 5. 1 strongly agree. 5 strongly disagree. There's the husband and wife's responses. Good question. How do we know this is going to be a t-test? What are some key elements of this problem that are letting you know this is going to be a t-test?
There's a data table.
Well, there's a data table for number 1. Now, for Thursday, I love that answer, and it's horribly accurate for Thursday. You can have proportional data in a table, though, in the world. Just so you realize, you can have counts and contingency tables and actually extract proportions from them, but not for Thursday, Rosie. Thank you for that. I try to answer not just for class, but also for the world around us. Rachel?
Their H's are being measured on a measure scale from 1 to 5.
Good. There's a measurement scale of 1 to 5, implying that 1 is lower than 5, 5 is higher than 1, and so forth and so on. Good. Good. I like that very much. We're not counting, we're measuring. Good. Very nice. There's also a key word up there, yes? You see the word average up there, yes? Look at it. Calculate the hypothesis to see if the average difference in the husband's versus the wife's satisfaction level is negative. And then they give you a parentheses, meaning that within the partnership, the husband is happier than the wife. Now make sure you understand why that would be negative. It seems like negative seems like it should be the other way around. It should be the other way around. Why would negative imply that we've got a happier husband than wife?
You've subtracted the wife's scores from the husband's scores.
Here's the deal. I think it's in the way they've written the verbiage here. They said difference in husbands versus wives. I think they've subtracted husband minus wife. I think that's what they've done, and here's why, Will. Here's why. Since smaller numbers are more satisfaction, smaller numbers minus bigger numbers are going to give you negative numbers. So we'd have to go husband minus wife to get a negative. If we go wife minus husband, we would therefore get a positive, which means you could test it that way if you wanted to. We could do it. We could actually run this test if you guys want to. Yeah, we didn't say yes or say yes, please run this test. Stop talking about it, just do it. Good. But let's make sure. Let's make sure we understand the verbiage there. Okay, so we understand why it's a t-test. We're buying why it's a t-test, testing an average. Okay, so let's templatize this thing out. Let's templatize this thing out. I'll put that back up in a second. Let's change what we have to change. Let's try my marker. Change what we have to change. We have to change most of this. Change that. It appears, does not appear. I am going to erase that, right? I have no idea what it's going to look like when we're done, so let's just do this. The claim is that the husband is happier than the wife. That's the claim. The husband's happier than the wife. Based on child care. All we have is a child care data. We have no other data besides. Pleased with the way we divide responsibilities for child care. What variable are we testing? Why is the camera pointed over here? I would demand a refund, you guys. What variable are we testing? Mu! What is mu measuring? What is mu measuring?
Population average.
Population average, good. Even more, average of what? Average?
Satisfaction.
Good, well, yes. Average difference between the husband and the wife, I think that's what we're going to have to test. I love the satisfaction, I love that, but I think what we have to do to make this a little more legit is look at the average difference between the husband's and the wife's scores. Average difference between husband and wife's score. So this becomes, try to make this feel like a problem from class last week. Which problem is this that we did in class? Now, it took us a lot longer to get the data for this one we did in class last week. Which problem is this?
The finger and thumb one.
It's the finger thumb, isn't it? It's the finger thumb. It's right? We have a couple that consists of a husband and a wife. We are pairing them up and seeing if there's a difference between each couple. Just like each one of you, we tested your finger and your thumb to see if there was a difference there, yes? It's that problem. It's that problem. So in other words, I'm going to add L1, L2, and L3 here. Tell me what's going to go where as we set this problem up. What's going to go where? L1, L2, and L3.
Wife's
think?
answers, husband's answers, and then the difference.
Taylor, give me it again. Give me it again.
Wife's answers, the husband's answers, and then the difference.
Okay, I love the difference here. I don't care who you put where here. It doesn't matter to me if you put husband, wife, wife, husband. Now, here's the deal. May I do it two ways, Taylor, if that's okay? Since I wrote up here the difference between the husband and the wife, may I put the husband's first here and the wife's first here? And then, of course, show you why it doesn't matter, as long as you interpret what you're going to be testing up here properly. May I do both ways? I think we have time for both ways. Is everybody see what I'm saying there? And more importantly, can you see why it would make a difference if I switched them? As I drop the lid. Okay, if you don't see, hold that thought. Hold that thought if you don't see. Because you'll see why once we start filling the hypotheses in. Okay. Mu is what we're testing. What are we trying to test to see? If who's more satisfied? Husband. We're going to go in believing
Zero.
that the average difference is zero. There is no difference on average between the husband and the wife. As we do with every hypothesis test, you go in believing nothing's changed. Okay. Now, what's going to go here? If it was not equal to zero, we would just be testing there's a difference between the husbands and the wives. This is a directional difference. The husband is happier. Why is it less than zero, Kayla? I agree with you wholeheartedly. This is going to be a less than zero test. Why? Now this is where you have to go back into the problem and read again. Oh God, you can't see that. Full screen now. Okay, read those words. Especially how the variables, how the values are defined. What numbers indicate more agreement with the statement? Smaller or bigger? Smaller indicate more agreement with the statement. And the statement is, I'm pleased. So if you have small numbers with an I'm pleased, that implies happiness with the statement, yes? So if the husband is happier than the wife, the husband's numbers are going to be lower. Good. Hold that thought. Hold that thought. Gotta read my ghetto up over here. We go. Boom. If we believe that statement, then the husband's numbers are lower than the wife's, which means we have smaller minus bigger, which equal negative, less than zero. Fair enough? Now, Kelly, I'm going to come back to this. What if we switched them up? Totally fine, as long as you then make that bigger than zero. And we're going to test both ways so you can see there's absolutely no difference. You get the exact same results. Fair? All right, thank you, thank you. Test statistic and p-value, this is where the data has to, we have to crunch the data now to figure this out. Right, let's do it. Let's do it. Let's fire this up. Get our data in L1 and L2. Do I need this? No, that's our times from Thursday. We can get rid of that. All right, husband's times. 2, 2, 1, 3. Okay. wife scores. Go. Small sample. Bother anybody? Small sample. Looks like we got 10. Bother anybody? Yeah, maybe. Maybe. Because it's a wide margin, right? Well, you've got a wide margin. By definition, you need a small sample. But that it might still be, oops, it might still be indicative of something. Let me do the little subtraction. Remember how to do subtraction in the TI? Put your blinker on top of L3 like that and just do L1 minus L2. Enter. It'll clear the whole list out and replace it with the differences. There are your differences. 0, 0, negative 2, 0, negative 2, negative 1, 0.
Sean, if you flip wife and husband and L1 and L2, you can just do L2 minus L1.
You absolutely. L2 minus that's
what I
right.
was thinking, yeah.
The exact, there's no difference. The only difference is going to be in the sign of the test statistic. That's it. The p-value will be absolutely identical because it's symmetric. Hold that thought. I'm going to come back and redo that one, Will, because I want Kaylee to see that what she said earlier is completely valid and it's the same thing by switching the signs. I just was trying to see. I want to make sure you guys understood why they were saying that negative implies the higher satisfaction. It's also confusing with the way they put the data, having the husband second. So wife's minus husband's would be positive. Kaylee, go ahead.
Well, I was just thinking the same thing as what you
Exactly.
said. Like, I was like, oh, you could just minus L1.
Yeah, of course you
L2
can.
from L1.
Of course you can. As long as you switch your hypothesis sign up top. That's the only thing I'm driving home here. Cool?
Yeah.
Because otherwise you get the complement of what you actually want, which is this is exactly the opposite potentially. Okay, here we go. Let's run it. T-test. T-test, here we go. Okay, this is getting a little bit busy up there on the board, yes? Slide it forward a smidge smaller. That's as good as it's going to get right now. Okay, we have data, yes? Yes. Mu naught, 0? Yes. Lists, L3? Yes. Frequency 1? Yes. Mu? Less than. We're grabbing a less than in this case. Yes, we're grabbing a less than. Because it's we're testing. We'll test it again with your guys' L2 minus L1 as well. Okay, let's draw it. Here comes the curve. There she is. I see my area down there, yes? The question is, how much area is there? I don't know. But I know that the test statistic came back as a T. Why is it a little T? See, because of the Guinness Brewery. T statistic we used back in the day with conference intervals. Same T distribution. T is negative 1.86. Well, that's kind of far. That's almost 2 full standard deviations. That's pretty far, yeah? What's the p-value, friend? What's the p-value?
Less than 5.
Less. Good. I love what was just said back there. Less than 5%. If you guys want to, you can just put less than 5% on your exams. You can totally do that if you want to. If you want to put the value down, it's about 4. That's an extra 0 there. It's about 4.76%. Your choice. Either put less than 5, put the p-value itself. Either one's fine. They both imply the same thing. What do they both imply? What do they both imply?
Men are more pleased.
Yes! That says the men are more pleased because this is small. Which means which of these two do we believe up here? Which of these two do we believe? That one. Which means it appears the husband are happier than the wife, even when including the wide margin of error. Even when including the wide margin of error in the data, the husbands are happier than the wives. I'm going to answer Kaylee's question real quick before moving on. If you had done L2 minus L1, everything would be the same. Watch this. Back to stat edit. L2 minus L1, totally fine. All the signs change. That's okay. Then you would go back and run the t-test, but just change that guy right there. And now watch what happens. This is kind of cool about this. When you actually graph it all out, you'll notice there's no area down there. But look at the area on the right side now. Exactly the same area. Look at the test statistic, it's positive. Now hopefully that makes sense. All you've done is you switched all the numbers and subtracted, instead of 1 minus 3, 3 minus 1. One's positive, one's negative, same magnitude though. Totally fine. Whatever makes more sense to you, I guess is what I'm at. As long as you make the sign up top agree with what you're testing. Fair so far? Okay, let's do some error analysis, yes? Could we be wrong? Could we be wrong? Good Lord, yes. Always. Let me fix this up right quick. Hang on.